Hey, welcome to the Explainer. All right, today we're going to dive into one of the most elegant and honestly, surprisingly powerful tools in machine learning, the naive Bayes classifier. It's simple, it's lightning fast, and I guarantee you interact with what it can do pretty much every single day.
You ever wonder how your inbox just knows how to filter out all those junk emails about some secret inheritance or a sale you just can't miss? Well, a lot of that magic comes down to a clever use of probability. And right at the heart of it is the very algorithm we're going to break down today.
And, this kind of thinking isn't just for emails. You can use it for all sorts of predictions, like, say, figuring out if the weather is good enough for a game of golf. What ties these two things together is this idea called classification.
So that really gets to the heart of the challenge, right? How do we teach a computer to make a decision like spam or not spam, play golf or don't play golf, when it has to look at a whole bunch of different clues at once? And in the world of machine learning, we don't call them clues, we call them features. Things like the weather forecast, the temperature, or whether it's windy.
So how do we solve this? Well, let me introduce you to our hero for today, an algorithm with a pretty revealing name, the naive Bayes classifier. And trust me, that name is going to tell you pretty much everything you need to know about it.
Okay, so let's break down that name. The Bayes part, that comes straight from Bayes' theorem, a really fundamental idea in probability. Basically, all it is a super smart way to update what you think is true when you get new information. It helps us figure out the probability of something happening based on other things we already know might be related.
But honestly, the really interesting part, the secret sauce, is that word naive. This is the algorithm's secret weapon. It makes one huge simplifying assumption. It treats every single feature as if it has absolutely nothing to do with any of the others. So think about our golf example. This model just assumes the temperature has zero effect on the humidity and the wind doesn't care if it's sunny. Of course, we know that's not really true, right? And that's exactly why it's called naive, but this one little trick makes the math incredibly simple and fast.
So to just quickly recap, the whole model is built on a few key ideas. The biggest one, like we said, is that all the features are independent. It also tends to assume that all features are equally important. And if you're dealing with continuous data, like an exact temperature, it assumes it follows a normal bell curve. It sounds almost too simple, but that's exactly where its power comes from.
Okay, theory is great, but how does this thing actually work? Let's get our hands dirty and build a prediction from the ground up. We're going to use a classic example, deciding whether or not to play golf based on the weather.
Step 1. We got to start by looking at our data from the past. You can think of it like a logbook where we wrote down the weather every day and whether or not we went golfing. The very first thing we do is figure out the overall chances of each outcome.
So let's just imagine we've got data from the last 14 days. On 9 of those days, we ended up playing golf. On the other 5, we didn't. So our starting or prior probability of playing golf is just 9 out of 14, and the chance of not playing is 5 out of 14. Easy enough, right? That's our starting point.
All right, next up, we have to dig a little deeper. We need to figure out the probability of each weather condition happening, given that we either played golf or we didn't. This is where we start connecting those individual weather features to whether we actually played golf or not.
So let's say the forecast for today is sunny, hot, with normal humidity and no wind. To make a prediction, we go back to our logbook. Let's take sunny, for example. We look back at all the days we played golf, all 9 of them, and we see that only 2 of those days were sunny. So, the probability of it being sunny on a day we play golf is 2 out of 9. We just do that for every one of today's conditions for both the yes days and the no days. And we end up with this complete table of probabilities.
Okay, now for the fun part. This is where that naive assumption really comes into play. Because it assumes everything is independent, we can literally just multiply all those probabilities together for each side of the question, yes and no. We'll do one calculation for the yes outcome and a separate one for no.
All right, let's tackle the yes case first. We start with that base probability of playing golf, which was 9 out of 14. Then we just multiply that by the probability of each of today's weather conditions for a yes day. So that's times 2/9 for sunny, times 2/9 for hot, times 6/9 for normal humidity, and times 6/9 for no wind. You plug all of that into a calculator, and what you get is our final likelihood score for yes, around 0.021.
Okay, now we rinse and repeat for the no class. We start with the base probability of not playing, which was 5 out of 14, and then we multiply that by all the likelihoods from the no column in our table. That's times 3/5 for sunny, times 2/5 for hot, times 1/5 for normal humidity, and times 2/5 for no wind. We run those numbers and we get a much smaller score, about 0.0068.
And believe it or not, the last step is the easiest one yet.
All we have to do is look at the two numbers we just calculated and see which one's bigger. That's our prediction.
And drumroll, please. The winner's pretty clear, isn't it? Since our yes score is way higher than our no score, the classifier predicts with confidence, yes, today is a good day for golf. And just like that, we have our answer. It's an incredibly powerful result from some surprisingly simple math.
So, now that we've seen how it works under the hood, let's kind of zoom out a bit. Because like any tool, naive Bayes is amazing for some jobs and, well, not so great for others. Knowing where it shines and where it fails is really the key.
So what's great about it? Well, for one, it is lightning fast and super easy to set up. It's also fantastic when you have tons of features, like trying to classify a document based on thousands of different words. And it can even work pretty well when you don't have a whole lot of data to start with. But the big catch, the thing you always have to remember, is that core assumption that all the features are independent is, almost never actually true in the real world. But even with that drawback, you can see why this thing is used all over the place. Its speed makes it perfect for the spam filtering we talked about at the beginning, but also for things like automatically analyzing if a movie review is positive or negative, helping doctors make an initial diagnosis based on symptoms, and even for credit scoring. It's a real workhorse in the world of machine learning. And one last thing that's good to know. This algorithm isn't just a one-trick pony. It actually comes in a few different flavors, and each one is designed for a different kind of data. There's Gaussian, which is for continuous things like height or temperature. There's multinomial, which is perfect for counts, like how many times a word shows up in an email. And there's Bernoulli, which is for simple yes-no features. Is a specific word in the email or not? So, this all kind of leaves us with a really interesting question, doesn't it? The naive Bayes classifier teaches us a really important lesson. Sometimes, the absolute smartest thing you can do is make a simple, even naive, assumption. It's just a great reminder that in a world that's always chasing more and more complexity, sometimes the most elegant, efficient, and, smartest solution is the simple one.